lunch. You will need some brain cells to follow along. Although overall it's going to be kind of a beginner-friendly workshop. We're going to do kind of a presentation first and then some Solidity coding. If you have some basic experience with Solidity, with smart contracts, or if you're just comfortable just reading code, then you should be able to follow along. So yeah, my name is Peter. I'm a protocol engineer at Scroll. And today I won't talk about Scroll per se, but I will talk about a new proposal that we proposed called RRP 7728 L1SLOAD. So this is a new proposal that Scroll kind of implemented in a DevNet, but we hope that this will be adopted by multiple L2s in the future. So the hope is that after this initial 20-minute presentation, you kind of get the idea, like what is L1SLOAD, what can you do with it, why should you care about it? And then for the remainder, myself and my friend RH will do like a Solidity kind of workshop. So we have two hands-on examples and exercises for you. Okay, so now you can hear me. I haven't said anything important yet, so yeah, let's kick off. Oh, by the way, before we kick off, if you have any questions, feel free to interrupt me, but also there is this Q&A function here in the app, so you can just click here. I think most people probably don't know about it. I don't think it's widely used. Feel free to submit any questions here as well. I will keep an eye on this. All right, so L1SLOAD is a new proposal for Rollups for L2s. It's a precompile that allows developers to build applications that read L1 state from their L2 contracts. We hope that this is a new functionality. It's not groundbreaking. This is something, if you're very technical or if you take on the cost, you can already do in your dApp. But this proposal makes it much, much easier. And we hope that this will unlock a lot of new applications. So I want to talk about what is L1SLOAD, kind of show you the interface, how to use it, what are some of the use cases that we found so far. Then I want to get a bit more philosophical, like why do we want to offer this service on the protocol level? And finally, just some insights into kind of the protocol engineering part and the challenges of designing such a proposal. There's going to be another talk on Thursday where I will jump into much more details about these protocol level considerations. All right, so what is L1SLOAD? So L1SLOAD, as I mentioned, is a precompile. If you're familiar with the EVM, you know that there's the EVM bytecode that you execute, but there's also special contracts called precompiles that implement certain functionality. On Ethereum, on layer 1, this is usually like heavy, expensive cryptographic operations that will be very expensive to implement in Solidity. But we can also use the same mechanism to expose other functionalities to L2 smart contracts. So L1SLOAD is a precompile, and you can call it from your contract, just normal Solidity code. And you can read state directly from layer 1, which is Ethereum. This is how it looks. How many of you are familiar with Solidity or has written Solidity? Okay, so I think you should be able to follow along. Basically, this is just a very intro example. The way you would interact with any precompile, including L1SLOAD, is basically you can just issue a call to it, like a smart contract call. Here we use a lower level call called static call, and you just encode the payload. And with this proposal, the payload is simply a contract address, an L1 contract address, and 1, 2, or more storage keys. You can call it from your contract, and then you can decode the result. So this is actually fetching data not from the local blockchain that you're running on, which might be Scroll, it might be Optimism, it might be Arbitrum, any L2 that implements this proposal. Instead of that, it's fetching data from Ethereum L1 under the hood. So this is defined in an RIP. I'm not sure if any of you are familiar with this. So EIP, Ethereum Improvement Proposals, are used to propose new features for the base layer for Ethereum. And there's kind of a new initiative this year called RIP, which is a similar process for Rollups. So Rollup Improvement Proposal. It's optional, so we can create these proposals. If you guys find it useful, then hopefully more and more Rollups will adopt this. Yeah, so just more details here. Why do we care about this? Why is it useful? This is kind of, as you say, it's kind of low level. Just looking at the previous slide code example, it's kind of hard to see what it's used for. Luckily, we've already run a couple of hackathons. And hackers came up with some great use case ideas in the past few months. And I think we have a similar hackathon just after Devcon. One of my favorite use case examples was a cross-layer tornado cache breach. So many of you might be familiar with tornado cache. It's a shielded pool. Basically, you can deposit your assets and then withdraw to another address, and you cannot correlate the depositor and withdraw address. So it's a privacy-preserving mixing pool. But you could only use it on L1, but you could use the same technology to kind of deposit on L1 and withdraw on L2, and this could be built using L1SLOAD. Another use case is ENS. So ENS is still primarily used on layer 1, although they are exploring, supporting more and more L2s or deploying on L2s. But if you're on a chain that doesn't have ENS, then through L1SLOAD, you can still resolve these domains just by reading the register contents from L1. There's also cross-layer reputation system incorporating data both from L1 and L2 chains. There's a bunch of DeFi application use cases. So for instance, you could borrow on L2 without bridging the collateral to L2, just using your collateral on L1. That's an idea that they explored. You could also implement these hooks for Uniswap to make sure that the L2 pool has enough liquidity and not too high slippage compared to the L1 pool. So kind of give more assurances to you when you swap. And you can also use other, multi-sig, A-wallet, key store use cases with this. So these are just some highlights, and I linked all of them here. You can check the slides if you're interested. These are very interesting projects that we've seen at hackathons. All right, so now you kind of have a general idea of what is L1SLOAD. So let me jump into kind of why we want to provide this functionality on the protocol level. I wanted to give a quick walkthrough of Rollups, but I think many of you were here for the previous session by Emily, and I prepared 2 slides, and Emily did like 50 slides, and she did a great job kind of telling all of you what rollups are, so I'm just going to keep it very short. So a rollup is an Ethereum that's inheriting a lot of security guarantees from L1, which is Ethereum in the case of rollups. So rollup create an L2 chain, and then package these L2 blocks into blobs, post it on Ethereum, and also post the execution results, which is the L2 state root. And then there's different mechanisms how you can verify the L2 state root towards a canonical bridge. So you can use fraud proofs, you can use ZK proofs. There's different pros and cons. So if you think about information relay between L1 and L2, when you relay information from L1, you need to usually use a deposit message or some kind of other message in the canonical bridge. And this message will be relayed by the sequencer in a verifiable way. So usually the sequencer would include these deposit messages where you can encode additional information, but the sequencer could also implement other functionality, for instance, relaying the L1 block hashes. The other way around, you usually need to first submit a withdraw message on the rollup, and then once this is finalized, you need to claim it on the L1 side. So slightly different ways depending on which direction you want to go. All right, so if you're a dApp developer and you want to read some data from L2 on L1, how do you do that? Well, you're lucky because you already have the L2 state root on L1. That's kind of an inherent property of all rollups that the L2 state root is posted to L1. So your contract can just read the state root and provide a Merkle proof, and then you can verifiably read any state from L2. The other way is basically the same thing, but it's a bit trickier because L2s usually don't have this notion of the L1 state root. So we would have to implement that first, but there's ways around this to implement it. And then it's the same thing. You provide a Merkle proof to read from L1. So it is already, without this proposal, it's possible to do it, but it's not very convenient. Like, how do you relay the L1 state root? How do you verify it? How do you provide this Merkle proof? It's a lot of extra complexity and overhead for the developer, as well as cost. So the idea here is all of this process, the second part, how to read L1 state from L2, is something that the sequencer could provide you as a service. So hide all the complexity from the developers, and you just focus on your application logic and just interact with this contract. So I would say it's Merkle proofs as a sequencer service. That's one way to think about it. If you think about this, how it's implanted by the sequencer, basically any call to this precompile is translated to an RPC call to an L1 node. So if you're familiar with the JSON RPC of Ethereum, there's one called eth get storage at, That's basically what this precompile corresponds to. And then the tricky part is how do you verify it? So we also need to make sure either in the fraud proof or in the ZK verification proof that you also verify this, that the sequencer didn't cheat you. The sequencer actually relayed the correct message. As an aside, many of you might not know, like, why do we use a precompile? Why don't we use an opcode, for instance? It's mainly because of compatibility. So we want to maintain compatibility with existing tooling, with the EVM, Solidity compiler. If you add the new opcode, then none of the tooling knows about it. But if you add the new precompile, then most of the tooling can interact with it as if it were, a normal Solidity contract. So it's a much less invasive way to add functionalities that Ethereum might not have. All right, just a little bit more details about kind of the implementation. Because as myself, protocol developers for Rollups and other Rollup teams, you need to think very hard about how do you implement it, what are the possible attack vectors that this could open up, how do you verify the inclusion, etc. So the interface of the contract that you will also see in more detail in the Solidity example is we try to keep it as simple as possible. So basically, you just need to pass an address, and then 1 to up to 5 in the current spec storage keys. So you can read up to 5 storage values from L1 in a single call to this precompile. And then the result is also just standard storage slots. If you're familiar with storage layout, then you know what this means. If you're not, then RH will tell you all about it in a couple of minutes. It's just returned to you, and then you can decode it. Implementation-wise, there's 2 main prerequisites that might be a bit controversial. So first, I briefly mentioned that you need to have this notion of what is the latest L1 block hash. Your L2 needs to have this notion. So either the sequencer needs to relay this with a special system transaction, or you need to have some other mechanism. But all the L2 nodes must agree on this, otherwise your execution would diverge. So I would call this feature trustless L1 block hash relay. Some rollups already have this. Others have designs for this, but not launched yet. In Scroll, the way it would work, and this might be different or similar to other rollups, is the sequencer optimistically relays this information, but any other node can verify it at this point. So if the sequencer cheats, then it's easy to detect. And when we finalize the batch with the ZK proof, that's when we verify that the sequencer actually relayed the correct block hash, because on L1, during finalization, we have access to this information. And the second prerequisite is that for reading L1 state, you need to have access to an L1 node, right? Which is already true for sequencer. So sequencer has to process these bridge messages. So they already connect to an L1 node. But currently, for some L2s, if you run a follower node, you don't need to connect to an L1 node. Now, if you adopt L1SLOAD proposal, then you must always connect to an L1 node. So that might be an additional overhead for some node operators, but I would argue that this is kind of acceptable. Yeah, so all L2 nodes then must connect to an L1 node so that they can serve these requests about L1 state. And then just 2 more notes about implementation. So we have a reference implementation. I have a link to this in the slides if you're interested in our Go Ethereum fork. But basically, what you need to do is pretty simple. So you need to modify the EVM and add this precompile so that when there's a call to that address, which is specified in the RIP, then it triggers execution of this special contract. And when this contract is called, it simply starts executing an RPC request against the L1 node and waits for the result. So there's some complexity here that I probably won't go into too much, that like what happens if the request times out or the request fails. This can be an issue, and also this request might affect throughputs. But normally when you run your L2 node on the same machine, let's say, or in the same data center as the L1 node, this should be fairly fast and error-free. And once the RPC returns, you return these results to the EVM, and execution continues as before. So that's the execution part, and the second part is verification. As I mentioned, we need to keep relaying these L1 block hashes to L2 in a verifiable way. So in our case, at Scroll, for instance, we have a Solidity contract on L2. The only thing that the sequencer does is that it takes the L1 block headers and feeds them into this L2 contract. And the L2 contract actually does the verification that it's a correct chain of L1 blocks. And then once you submit this to L1 and verify it in a ZK proof, then we read the block hash, the correct block hash from the L1 EVM context and verify that this relay step was done correctly. And finally, so this first and second step is the trustless block hash relay component, but you also need to verify each and every call to this L1SLOAD precompile. So for any precompile call, we need to, or the sequencer or the prover, depending on your architecture, it needs to fetch an MPT proof and it needs to verify that as part of the broader ZK proof. So this is something, all of these steps are steps that you would need to do as a developer. But now that this is part of the protocol and it's a sequencer service, you don't need to care about this anymore. You can know that it's working and verified. All right, a lot of details, just a few more notes about the next steps. So this RIP is fairly new. We just published it in June this year. There's a call for the RIP process called roll call. We presented it in July. And then, as I mentioned, since July until now, we had a bunch of hackathons where hackers and devs could explore this and play around with these proposals. And for now, we just want to continue this process, and we'd love to hear more feedback from developers, from protocol maintainers. Basically, once we can converge on a spec that everyone is happy with, and other L2 teams, at least 2 or 3 L2 teams have some willingness to adopt it, then we can finalize the spec and start rolling this out in production. I think it would be awesome to get to that stage next year. All right, there's a few additional resources here for your reference. And I have, again, the slides here if you want to save them. But for the remainder of the talk or the workshop, we want to jump into more like hands-on coding. Before we do that, any questions? Yep. Yeah, so when you have a transaction that calls L1SLOAD, then any node, be it sequencer or follower node, will execute an RPC call corresponding to this precompile call. For the validation. Yeah, so proving, it depends on your proving system, but I think we can say that, so the question was how long does it take to verify the whole thing? A couple of years ago, this would have been impractical because you couldn't have proven an L1 MPT proof in ZK. The technology was not there yet. But now proving speeds have been catching up and you have general purpose ZK VMs. So in our experience, this would add maybe a couple more minutes to the proving time. But it's not significant, and it will go down rapidly in the next few years. All right, there's a question here. Thanks for using the Q&A form. So what's the adoption look like from other L2s? How do we help? That's a great question. So we presented it at Roll Call. There's been some discussion on ETH Magicians, which is kind of the go-to place to discuss the proposal, but we haven't received too much feedback. The main feedback we've received so far is that devs love it. It kind of opens up the design space to devs that you would not think about normally. So that's very good feedback, but I'd love to hear feedback from other L2 teams, other Rollups teams. If you can point out issues or anything that might break in the spec that we need to fix, the earlier the better, and then we can converge to a final spec. All right. So I'll just continue with the next section. So we have these code examples, basically 3 code examples of increasing complexity, although not too complex setup. If you want to either follow along, well, if you follow along, you can just follow the screen. If you want to reference this later, then you can take the code from GitHub. It has all the solutions, so if you don't want spoilers, then don't open it yet, or don't open the files yet. All right, so you can see the editor. If the text is too small or anything, then let me know and I can adjust. So I want to walk you through a very simple kind of toy example. just kind of to get a feel of how L1SLOAD works from a developer perspective. Let me show you. So for this example, we will use Foundry. Many of you might have used, Remix, Hardhat, Foundry. I think more and more people use Foundry. That's what we're going to use here, but you can use any of your developer tools that you're happy with. We're just going to do some fast development and testing on Foundry, and then RH will show you how you can also interact with a DevNet that we're running. So the simple toy example that I want to talk about is a counter. So let's say we have this simple counter contract on L1, and it maintains 2 entries in storage. So one is a simple unsigned int, and the other one is a mapping. So nothing fancy yet. And then there's only one function on it, which is to increment this number, and then to store something in the mapping. I guess counter is a bit of a misnomer because there's also this mapping, but you get the point. We just want to have kind of some state on L1 that we can interact with. So let's say you deploy this contract on L1, or someone has deployed it and you want to read from it. How do you read from it from L2? So for that, we will define another contract called counter reader. And the idea is that this is deployed on a different blockchain. This is deployed on L2. So let's say counter is deployed on Ethereum. Counter reader is deployed on Arbitrum or zk-sync or any rollup that adopts this proposal. So when we instantiate this counter reader, we definitely need to have the address. So I have that pre-filled in here. So we're going to store the address of the L1 contract. And then the question is, how do you actually read from the L1 contract? So I'm going to show you first the low-level interface. And then we also have some helper kind of utilities that make it much, much easier to do this. So let's just go back to the slides for a moment. I had this slide previously. So this is a recipe of what you want to do. You need to ABI encode using encode packed the arguments to this call, static call, and then decode the result. So let's try to do this and see if it happens. So I'm just going to start by defining the payload. And the payload is, as I mentioned, it's an address. And we already have the address here stored. That will be counter. I could also call it L1 counter just to make it clear. And then it can be 1, 2, or up to 5 storage slots. So let's keep things simple and just focus on the first variable for now. Now, who knows what is the storage slot of this variable? Yeah, 0. This is quite easy here, but when the contract gets more complex, then it also gets more complex, like if you have inheritance, etc. So one thing you can do is, I usually use forge inspect. It's a kind of handy command. So you can use forge inspect, storage layout. I believe this basically just calls into the Solidity compiler, and this will show the storage layout of your contract. So we have number at slot 0, and the mapping is at slot 1, as expected. So I'm just going to go ahead and read slot 0. And that's going to be our payload. So we have the payload. Next step is to actually call the precompile. So to call the precompile, you need to have the address. Here in this helper, I already have this hard-coded. This is subject to change. So as I mentioned, the proposal is still not final. And also there's an interesting discussion going on, like what address should these L2 precompiles use? Should they continue at the same address range that L1 precompiles have? Or should they have like a dedicated precompile address range? I think everyone is leaning toward the second option. But for now, we're just going to use the same address that we have on our DevNet that we're maintaining. So we're just going to use this address and static call payload. And what this returns, if you're familiar with kind of lower level calls inside the EVM, is whether this call succeeded and the result of the call. All right, so we're halfway there. I'm going very slow because this is kind of an intro example. I think for advanced Solidity developers, this might be a bit boring, but just hang on for a moment. So you got to make sure that this call succeeded. If it did not, then of course we cannot continue. Now it depends on the final spec. In the current implementation, there's no way that the L1SLOAD fails. Once the transaction is included in a block, that means that the sequencer managed to fetch these storage entries, so it should always succeed. But unless, of course, you, for instance, encoded the inputs incorrectly. So you gotta make sure that you do that right. So if it didn't succeed, we just revert. And if it did succeed, then we can decode the data. So the data, very developer friendly again, is just ABI encoded, so you can use all the Solidity tooling or syntax to decode it. In our case, for now, this is going to be a single unsigned int. So this is the number, and I can get to the number by just ABI decoding this return value. All right, so we got to a point where we could read at least one of the storage slots. Now let's try to test it. And the test kind of also shows you, first of all, how you can develop with L1SLOAD, and also how this toy example would work in practice. So I have a Foundry test prepared here. Kind of the very convenient thing about Foundry is that you can use Solidity for the whole development process. You don't need to switch to another language to write your tests. So in this case, we do run these tests in Solidity, but the problem is that Anvil and Foundry, all this tooling is not aware of this L1SLOAD precompile. So to make development painless, we created this class that you can use, or this contract test with L1SLOAD. So this basically injects fake L1SLOAD that behaves the same way as the real one into your test environment. So whatever you test with this should also work in the actual L2 context. And then the test itself is very simple. We just deploy the L1 contract. You can imagine that this happens on L1. For now, we're testing it in a single EVM environment. So deploy the L1 contract and deploy the L2 contract with the address. And then you try to read the contract. Originally, we didn't initialize the storage values, so all of them should be 0. Then we call increment. After this increment call, when we read from L2, you should see that the state has been updated. Let's see if that works. Oops. All right, so far so good. So we ran the test, it passed. And that means that actually when we called this read counter method, what it did is it called L1SLOAD. L1SLOAD fetched this storage from L1, and then it's returned to the L2 context. The only thing missing from this example is how do we read the mapping? Because if I uncomment this line, since we didn't implement this, the test will fail as expected. So how do we do that? Does anyone know? So basically what we want to do is read the mapping value of this corresponding to this key of 1, 2, 3. How do I get the storage slot corresponding to this value? I wonder if anyone knows. Hash of the message sender? Hash is correct. Exactly. So some way you need to take the key, you need to take the slot, which is 1 in this case, hash them, ABI encode and hash them together, and that's how Solidity calculates these mapping keys. So it's a bit more complex, but if you know what you're doing, then not super complex. So let's try to add that. I just move this to another variable. Oops. It's actually quite hard to type standing here. Just hold on for a sec. So you need to ABI encode. I believe the first one is the key. It's something that you kind of got to remember, but RH will enlighten you in a couple of seconds about the details. So first is the storage key, second is the slot, and then you just take the hash. And let's see if that works. Maybe I remember it incorrectly, in which case I can just fix it. All right, so now instead of reading 1 slot, I read 2 slots. The call otherwise happens the same way. I just need to add this additional argument here. And also when I decode the results, I need to decode it as 2 unsigned ints. So this will be First one is going to be, let's say, value 0, and the second is value 1. And then just return this. So it's not fundamentally different from just reading one value or two values. Okay, let's see if that works. So now the test should pass. Yeah, question?
Yeah, but question or observation about the design of this. Like, for example, if you are want to read something on the same layer in a contract, one thing we can do is basically instantiating this contract at a certain address and read the data of the actual contained in this contract. So I was wondering that maybe this thing should be designed in the same way where you just specify, okay, I want this contract instantiated on layer 1 instead of layer 2.
Mm-hmm.
So basically in this way you don't have to specify the slot.
Oh yeah, yeah. So that's a good point. I think the feedback is this is kind of low level. Like, who wants to deal with this? We could, if we could just call counter dot number to read it, this would be more convenient. And you can definitely do that. I think L1SLOAD is just a building block, and it's very easy to build higher level abstractions on top of that. Actually, let me show you, and then we can get to the next question. So just wanted to show you this is how it works on a low level, but we do provide some libraries, a simple library in this repo if you open it. So instead of what you can do is L1SLOAD read unsigned int and just provide the address and the slot. So I still need to define a slots, but the rest of the code is basically replaced by this single liner. So same thing, actually, just hidden in a library. So as a developer, it's probably much easier to interface with this. And also, we have utilities for unsigned int, for bytes, for address, etc. And also, this is still not as high level as you suggested, but using this is very easy I can create a contract or generate a contract that looks just like this, but is actually calling L1SLOAD. Your question? Yeah. That's a really good question. The question was, can I specify which block I want to read from? Yeah. So that's a big challenge for sure. So in the first iteration of the RIP, we designed the interface in a way that you can also pass a block number, so you can read from arbitrary height. That's for some applications that's a must-have. For many applications, this is not needed, and it also requires you to run an archive node because you need to be able to always serve archive data. But basically, one of the open questions for the RIP, like, do we need this? Do developers need this? If yes, then we can add this. But in terms of reading stale data, that's still a challenge because there's a delay between when the data is updated on L1 and when this information is relayed to L2. So this delay can be reduced, but it's not instantaneous. Exactly, yeah. Someone commented on ETH Magician exactly about this. If you have any input for that discussion, we'd love to hear or see your comment. Any other questions? Actually, let me check the Q&A. We can get back to the more general questions a bit later. So that kind of wraps up the first example. Again, a very simple toy example, but kind of shows you the power of L1SLOAD and also shows you how you can use this in your application without too much added complexity. Now for the next two sections, I want to hand it over to RH. Hopefully, I think many of you might be dozing off, my mellow voice and also digesting the lunch. So RH is full of energy and he'll kind of shake you up. Yeah.
So Peter's too tall. I have to just adjust this a little bit. So, hey everyone, my name is RH. I am so happy that Peter went first because mine is going to be dialing it down a lot level lower. To the extent that because it's a beginner workshop, we're going to be tailoring it for beginners who probably are not very familiar with Foundry as well, but they also just want to get rapid prototyping accessibility by using Remix. So, we're going to be using Remix a lot. Shout out to the Remix team. And we're going to dive into the example first. Okay, while it's loading up here, I'm not too sure if I would be getting like bandwidth or if the demo gods are gonna be with me. So what I did over here was that I pre-recorded this and we could go through this. It's probably about 10 minutes, and then I'm going to be narrating over it as well. So 10 minutes, this is going to be like super beginner friendly. So for a lot of you, I'm seeing intermediate to advanced level devs, you're going to be bored out of your mind. And if you're bored out of your mind, hopefully I can sing you a lullaby and then put you to bed for a little while, take a little nap, and then be back up for a bit more of the complex types that we will be seeing. So in this section, in part 2, just a quick overview as well. We have done 3 hackathons so far, which uses L1SLOAD. So through those hackathons, we have received like multiple feedback on implementation, understanding how to rapidly use it in different hackathon environments so that you can quickly tap into it and start building the application that you're looking for. So that is sort of where I will be leading this session, more so for like the implementation side of things. Alrighty. So let's jump right into the Remix demo first. This is going to be covering some setup in terms of like how do you want to set up your injector provider environment in MetaMask with the DevNet that Peter mentioned. We're going to be going through that. And you're all also in for some treat to watch me do a bit of debugging and watch my poor coding skills all on screen. And just before we dive into it, I want to give a quick shout out to Ahmed. I see Ahmed there in the crowd. He was the one who helped us to also put this together. So a lot of the credits go to him. Okay, so without further ado, we're going to first jump into Remix. So this is me writing the L1SLOAD demo.sol. Is this like, how fast is this? This seems like super fast. Let's do fast. Okay. All right, now I know that it's a little small because even I can't see it from here, so I've enlarged this. So in this L1SLOAD demo, I'm going to do a quick demo on how you can rapidly create a layer 1 contract and a layer 2 contract. Just read L1SLOAD with less than 25 lines of code just to see how simple it can get. So for this context over here, we are creating an L1 contract. So this would be on Ethereum mainnet. And in this case, since we're doing a prototyping version, it's going to be on Sepolia, we're going to be defining the first variable over here, which is number of type uint256. And we're going to be putting up a setter function. So this setter function over here is for us to override this number variable. And as we can see, number is equals to underscore value. And that's all that is required for the L1 contract. Again, this is a very, very simple example. We're probably going to be speed running through this because Peter did a way cooler job with Foundry. But this is also to cater to developers who are more accustomed to using Remix. So now moving on to the layer 2 contract. Yeah, fun fact about Remix, we can actually put layer 1 contract and layer 2 contract also in the same file. I found that like pretty cool. So the layer 2 contract itself, like what Peter mentioned, it could be an Arbitrum or whatever type of rollup in the future that decides to adopt this piece of technology. So very quickly, I am already defining the L1SLOAD precompile address over here. Again, I'll be sharing all of the resources on where we can find setting up for your DevNet. It's all here. So I'm just like typing it out, l1sload.scroll.systems. If any of you are bored right now, I'm just putting it up here also on the screen so you can also be very handy with checking out the resources that we have. There's a specific section here, DevNet, and it has a table outlining every type of information you need in order to get set up with interacting with the DevNet. And there you can see that is the L1SLOAD precompile address. And again, over here right now, we're going to be building the getter function for it. And this getter function will be the one where we call the number from the L1 contract. Again, this is me trying to be as verbose as I can, but at some part, not really. I think I do a pretty bad job. So you can come and provide me with constructive feedback later on. And we're going to be creating 2 arguments over here. We have the L1 contract address because we have to ultimately decide which is the contract address that we're reading into. And we also have to define the storage slot number. And over here, since it's a getter function, we're going to be returning a uint256. And oh yeah, this is just me showcasing some Remix functionality. Again, we're diving into like what you can also do in Remix here. So moving on, I've also written some comments on like what I'm about to do next. Probably should have done it in more like a to-do fashion. But anyways, we're writing a call function to L1 contract. We're not really defining the payload over here. I'm just trying to see what we can do with less than 25 lines of code here. So I try to be creative, not really. And over here, we are destructuring already this low-level call. And we are going to be packing the arguments, which in this case, it will be the L1 contract address together with the storage slot number. And then eventually, the destructuring of this process will return a Boolean of like the success and also like the payload. In this case, I'm defining it as uint data. And very similar to Peter's example over here, we will be defining like for success, if it's failing, and it's going to be reverting with an error message over here. Okay, I promise you, we've wrapped up really, really soon. Now we just have to convert the bytes. We have to typecast it from bytes to uint256 over here. So this would be the syntax in order for us to typecast it to uint256. So over here, very quickly, just now you saw my wallet address, and it's already set up to be with Sepolia network. So we're going to deploy this contract directly to Sepolia. And yeah, this is me being a lot more verbose. Now we're deploying L1 contract to Sepolia. So really, really beginner friendly here. We're like tapping onto like the entire spectrum of even aspiring developers here. Okay, so now we've deployed it. Oops. And after we've deployed it, it's probably a really good idea for us to also copy the contract address, which I did not do, but you can kind of see how the terminal from Remix would help us to gather that information later on. So I'm setting the number here to 7 just because we're at Devcon 7. Haha, found that was like pretty cool thought process, probably just myself. So right now, number is set to 7 on the layer 1 contract itself. So now we're going to set up our custom network for DevNet. We're going to go through this process of how it can get set up. Over here on the top left, you should be able to see like add a custom network. So over here, you just populate the information of network name, RPC URL, everything. You can just copy and paste it from DevNet. It's all set up for our convenience. There we go. So this here, I've already preloaded the address for Sepolia ETH. Now for developers who are interested in trying this out, the faucet is here. Definitely recommend you to check out the faucet. You get 0.1 Sepolia ETH for DevNet, and it allows you to like tinker with as much as you want. So over here, now that I've already added this custom network, we would then be able to directly deploy it onto DevNet. So that's us switching to L2 contract, and then we can directly deploy. Over here, I'm going to be showcasing as well what were some of those errors that I've encountered, so being very transparent as well. Notice that there is the transaction failure for not having enough gas. I'll also just be showcasing to some who are newer to Remix and also aspiring developers of like what you can do in order to get this to go through. So then we just have to bump up the gas. So what I just did was I just bump up to 1. Very, I would say, a simple way, a smooth brain way of treating this. By bumping it 1, then we are able to deploy the contract. So right now we already have this contract on L2. So over here, we're going to be passing on those to the argument, the input to the argument. Over here, we have the L1 contract address. So in retrospect, in hindsight, I should have like copied the moment that the contract was deployed on Sepolia. But even if it's not, you have a record of the past transactions in your terminal in Remix over here. Pretty handy. You can see that the contract address, if this would go away, is just directly tied to this contract address key here. So you can just copy that, and then you can just pass that over to your L1 contract address and storage slot number. Peter has done a great job already. Everyone here is like GigaBrain as well, so you already know that this is like storage slot 0. So I've also tried to be a bit more verbose so that people know that it's 0 index for how EVM treats storage slot. And you can see that we have successfully called 7 as the number, as a response. So we're able to get that information from the L2 contract. So there was also one thing that was lightly touched upon for the L1SLOAD technology itself. So if let's say if it is in production, if I'm not wrong, it takes about 10 minutes in order for us to retrieve the information on L2. But if on DevNet, there's actually an artificial simulation, so it's actually relatively quicker in order for us to get the information. But over here, you can see that I'm trying to set a new number to showcase that it actually takes some time before we're able to read that data due to us simulating the L2, the delay of the time that we're getting the information from the L1 storage slot itself. So right now on L1, you can see that the number has been updated to 100. But when we're moving back to the L2 contract, it's going to take a little bit of time in order for us to get the latest information. So as a developer yourself, when you're building in Hackathon, if you come into this part where, hey, why am I not getting this information? It's like better documented inside the L1SLOAD.scroll.systems as to a bit of a delay for us when we're getting this information. But I can assure you that I would say it's almost about 20, 30 seconds ago, or around there for the time of my testing. This is me just like repeatedly pressing it in a way that I'm showing you that I'm actively interacting with the UI here. But eventually, sometime about like 20 and 30 seconds, you'll see that the U256, it will be updating itself to 100. So I think it should be now. This is also me going through the different types of transaction that we see. Yes, so it takes just a little while for it to update its information in order to get the information from the L1 contract address. So just like bear in mind when you're also building using like Remix, if let's say you encounter this issue, there's an L1 block import delay time. Yeah, it's better documented here. Feel free to also like check out the resource here. So this is actually me going through a very elementary way of what it's like interacting with the L1SLOAD technology using Remix. So maybe I can pause here a little while to see if anyone has any questions. But I think like Peter done a greater job, and then he's covered like all the possible questions. So now what I think we can do is I want to touch on product refinement a little bit. And what I mean by product refinement is in the previous hackathons, we have different developers also trying to use different type of data types and different types of structures which are a lot more complex. We're going to dive into it and see how you can immediately implement it inside your code in the upcoming hackathon or whatever hackathon that you're looking at, or even if you're looking to just like build some cool shit, right? Am I allowed to say that? I hope so. But anyways, going into this, hopefully this is not too small. Let me enlarge this. Okay, so this is a pre-written contract. In order to like facilitate this discussion, what I've done over here is I also have a couple of contract addresses here, and I'm just going to be using them and load them in directly into our L1 contract. So over here, we have the first one, we have L1 contract. Okay, so for this demo over here, we will load this in directly into Remix. We're gonna pass that contract address, and this should be what you will see. Now again, all of this information, I want to highlight that it's already in the QR code that Peter shared. We have all the information over here, Devcon L1SLOAD workshop. If you head over to source, and if you head into part 2 of the workshop, you'll be able to get all of the code here directly. So at the same time, in a way, you can actually be interacting with this as I am going through this demo with everyone over here. So very quickly, while we're just reading through this contract, we can see that we are defining U256. There's a variable for it. And then there's also L1 text is what I've called it for string, and also bytes32, which is for L1 bytes. And some of them, I have left the comment, it's like storage slot at position 0, storage slot at location 1, storage slot at location 2. But the subsequent one, we're going to try to have a bit more of an interaction together with the crowd here. And you guys let me know what you think of the storage slot for the subsequent ones. We'll dive into them like later on. So we'll be also looking into fixed array and also array with smaller data types, for example, like a UN64, and then also with dynamic arrays. And then we're going to look at mapping, nested mapping, and also struct. So these are some of the data types and structures that we're using out there. Definitely there's a lot more complex ones as well, like what Pierre mentioned, there's also inheritance. But for the sake of time, with respect to the time that we have, now it's 2:50. Okay, we will be going through this example that I have. Again, it's a accumulation of the past hackathons that we try to refine the ideas upon. And for this constructor, very quickly running through with everyone. For L1 fixed array, we have already instantiated a contract with several input already. So you can see all of them inside here. L1 fixed array goes with like in the array of 3, 6, and 9, fixed array 2, 10, 20, 0, and 30, and so on and so forth. And the following ones, these are just setter functions and then also getter functions for us to kind of play around if you're interested. I know that in hackathons, it can get pretty, I would say, stressful. So you just want something quick and easy, copy and paste and start testing things out. So over here, we're just going to take a look at what it is like when we are interacting with the contract already. There are some parameters that I have already passed. So I think the state right now, it should be reflecting what it is. So for example, when we're getting retrieve number, you can see that, is it too small? I hope this is not too small. Okay, maybe this is better. So uint256 itself, for the variable of L1 number, it's already been instantiated with 100 over here. So there are a couple more. We're gonna go through my favorite, which is retrieve string. Retrieve string here, this is interesting. I love Devcon. I am super excited to be here with all of you. Devcon is gonna be the best time of our life. All right. But it's very interesting as well, because for string type, we're going to see how we can actually access the storage slot to concatenate all of the string, because as we know, it's only a uint256 for each of the storage slots. But for what I have passed over here, it's definitely like way more than that. It's not able to like store all of it. So how do we actually concatenate everything and then actually retrieve the string that you want? Because there are some hackathon use cases that I've heard of developers wanting to also add maybe like a URL to create like different types of profiles, and then like have it live on like L1. So this is why we have the example for retrieving string and how do we like concatenate all of it. And if we don't, what happens? We're gonna be going through some visual illustrations of that as well, because the best way to show is by, visual representation. And then for struct, what we have set in place is that we have, let me quickly go through the struct over here. We have the name and we have age, and then some of the information that we have already put in place is like Alice is 20 years old, Bob is 21, Charlie is 22, and these are the 3 pairs that we have. And then very quickly, a quick run through as well. If we retrieve bytes, you can see that this byte is not all zeros. You've got 1, 2, 3, and 4, 5, 6. For the sake of time, I've already run some of this information. I've already spit it into this like contract address over here. So, which is why you can see that this information, they are not just 0. If let's say it's just instantiated, you're gonna just be seeing zeros. And if let's say we retrieve like a dynamic array, again, we have instantiated it over here. You can see that it's 100, 200, 300, 400, fixed array 369, and also fixed array 2, 10, 20, 0, and 30. So we can kind of see that, I'm not lying, this is my proof of work, that I've done my homework. Everything here, it is correlating to this address which has been instantiated. Okay, so that is a high level starting point to get everyone accustomed to what this contract look like when we're trying to call it like using Remix. So now, onwards to the fun part. The fun part would be to look at L2 contract. How do we actually interact with L1 contract? And for this example, I have also deployed the contract already, because I feel like demo gods are never always with me. So I just try to prepare myself as best as possible so that everyone have a smooth brain experience, just like me. Okay, so for 2 of this contract here, we have the basic L2 contract.so, and this is going to be touching on more of, I would say, just 3 data types that we're looking at. We're going to have a retrieve for L1 number, which is the L1 number. And then we also have the L1 string. And then we also have the L1 bytes. These are just the 3 data types that we're looking at. So I would say this is probably the beginner version before we move into the more advanced type of manner of us calling the different, more complex data types and data structures. So for L2 contract, what we're first going to do is we will first change our network. And for network, I have this as scroll L1SLOAD. And we will also just copy the address which has been deployed over here. Again, we're just working with Remix over here, so everything is, already set up. Okay, so for retrieving L1 number, so what we're going to do right now, we are going to be reading through the contract together with everyone. Again, there's like multiple ways of us actually setting this up. We can even use the contract that we're planning to read and pass it on as an argument to the function itself. But for the purposes of this demo, in order to kind of like speed run this as well, what we have done is we're instantiating this contract directly with the L1SLOAD contract address, in this case, which was the L1 contract previously that we've seen here. So in this case, when we call retrieve L1 number should return us 100 over here, yes. And so when we take a look at Peter's demo as representation, basically I didn't exactly define the payload as a line by itself, that's the only difference, but everything else remains the same, right? So a lot of the pattern, this is me going through the same patterns, running it through in a recursive fashion. So you can kind of see that actually utilizing this technology is not very difficult, even for aspiring developers. This is what I would like to try to instill to everyone here in the audience, I would say. So we're retrieving L1 number, public view returns U256 over here. The slot number, over here, I have defined it already in the local variable as 0, because in the L1 contract, again, L1 number variable, global variable is at location 0. And in order for us to destructure this call here, it's a very standard syntax, I would say, for us to destructure the information. We get the payload, which is data, and then after that, we typecast it to U256 in order to get the result of 100 here, which has been set in L1 contract. Now, okay, L1 string, I'm going to touch on that a little later. I have bytes underneath here first. So we're going to touch on bytes first. Very similar also. Again, the only difference is that what we're returning right now is then bytes memory. And for the slot number, for the L1 slot number here, it's at location 2, I would say. So this would be what we would be officially passing through to it. And when we are calling, we're making this low-level call, we're essentially calling this address here, this L1SLOAD address is reading from here that we've defined in the global variable. And we can create this low-level call, and then we pack all the information, the contract address and the slot number, we concatenate both of it in code pack, and then we make this call to effectively retrieve the data, which is in the form of bytes. And when we call it, we can see that it is exactly reading to what was the L1 contract result like. Now, for string type, I find that string is quite an interesting piece of information. I've heard some of the audiences are already very familiar with how to actually retrieving the information. So I feel like there are a lot of like intermediate and advanced level devs here already in the audience. So this is like fantastic also. And what we're going to do is just kind of like rehash some of these concepts that we have seen. And for string over here, I mentioned like test slots, for example, because there's a limit for us to store information in each of these storage slots. It goes up to like only U256, for example. And so because of that, there's like limitation for each of these storage slot. What then happens is that we actually have to add we have to create a while loop in order for us to concatenate all of the string information together and then return like what we have initially like passed at the start of it. So for example, right now, string storage slot is located at location number 1, but if we were to pass on maybe the test slot of 0, because it's always going to be indexed at 0, you can see that what it's returning is I love Devcon, I'm super, but then it stops over there. But if let's say we were to create a while loop for it, so as long as while it's true, we are able to concatenate all of the string data together, it should be able to help us concatenate the entire string result together and give us what we have passed. Like, I love Devcon, I'm super excited to be here with all of you. So that was me like speed running it. So let me dial it back and then we kind of see step by step of how we actually retrieve the L1 string. So over here, the L1 slot number is still at location number 1. The slot sequence here, I've noted it as 0 because it all starts at 0, but eventually we're going to add the sequencing to just keep adding it incrementally so that it can fully concatenate itself. We're going to be defining string memory string result as empty at the start of it, and while it's true, again, we're going to be making a low-level call over here, and this is where it gets a little bit more interesting. We have the L1SLOAD contract address, but I've heard some from from the audience mentioning that we have to hash it. Exactly, that is correct. We're going to hash it, and then we're going to typecast it to uint256, and then we're going to add the slot sequence to it. So whenever that is true, we're going to incrementally increase the slot sequence because we know that there are still more information after that slot. And what it looks like is because if us hashing this data subsequently, if let's say it returns similar like 0x0000, it will then break. But before it breaks, as long as it stays true, it's just going to concatenate everything and return the string result. So this is like a high level of how we can actually concatenate everything and retrieve the L1 string result here. Okay. So again, all of this information, we have this code directly available inside the L2 contract here. So for devs out there who are excited to just get started with like tinkering with this, here's one for all of you. Okay, and then for the third piece, third and final one, I know, I'm putting everyone to sleep right now. We're gonna try to make it fun for the last one. Okay, so for the last one over here, we have the L2 contract advanced type here, and we're going to replace this with this contract. All right, so for this here, it will be a lot more interesting because we'll say that this is a bit more complex with different ways of actually querying the information. But very similarly as well, we're still defining the L1SLOAD precompile address up front over here already. And the L1SLOAD contract address is because when we're instantiating this contract, it's directly using the L1 contract address, and so that it stays as a global variable here. We're also defining the L1 profile struct already, which means that we kind of need to create the data type for what is an L1 profile struct. Take it in a way that we are creating profiles for our people. This is a simulation and an example of this. So over here, if let's say we were to retrieve fixed L1 array, we're going to be walking through the first information, I would say, retrieve function step by step. We're passing the variable storage slot. In this case, this variable storage slot will be referencing L1 contract where this storage slot location is. And then afterwards, similarly, because it's an array, the way to access it is that there's going to be subsequent location that it is stored in. So what I've done is we just like add it in. Of course, there's like different ways of approaching it, but I felt like it was a fun way to also get the audiences like engaged to see where people think the storage slots are. But everyone's so smart, so I think they're gonna get it. So very quickly, if I were to just kind of get the audience to think about where do we think is the L1 fixed rate storage slot at? This is storage slot 3. Dang, that's good. All right, 3. Okay, and maybe just a quick one. We're going to plug this information in if we are going for retrieve fixed array element here. And we say that the storage slot is storage slot number 3. And then array slot would be, we'll say 0 because it's all 0 index. And we call it, you're going to get 3 because 3 was already instantiated in the contract here as position 3 as well, storage slot 3. But what about for 6 and 9? Where is the storage slot for 6 and 9? 4 and 5. I hear 4 and 5. That's cool. So let's give this a try. We can go to the contract here. And because what I've done is, one way to think about it is it's just going to be added sequentially during the contract instantiation. So when we are creating the contract, already deploying it, there's like 3, 6, and 9. So 3 itself would be occupying one storage slot, 6 would be occupying another, and 9 would be occupying the subsequent one. So what I've done here is that when 3 plus 1 is essentially storage slot number 4, and you're going to be retrieving 6 as the return result over here. And the way to access this information, you're going to start seeing very repetitive type of syntax. It's also encode, it's using ABI encode pack, where we access the L1 contract address, which is from L1 contract. And then in this case, it's just a variable storage slot plus array slot. Again, we can always argue that we don't need array slot. The reason I've added that in here is just to show what we're really thinking about. We're just like adding the array slot based off of the length of the array. But in this case, actually, for variable storage slot, we could have just mentioned that this is variable storage slot of 4, but the array slot, let's just say if it's 0, we should still just be getting 6, because technically this is storage slot of 4. Yes, so we'll still be getting 6. Subsequently, if we look at dynamic array gets a little bit more interesting because during contract instantiation time, it's more of the length of the array that gets recorded into the storage slot itself, but the data itself is stored somewhere else, which we will need to access it differently. So if we look at this low-level call over here, it's actually ABI encode pack, and then we have the L1SLOAD contract address, and then we are hashing this variable storage slot, and then we are actually adding subsequent array index on top of it in order for us to get this, to retrieve the dynamic array number. So if we were to look at an example over here, if we look at L1 contract, so we jumped into like dynamic array over here. Yes, we jumped over to dynamic array. Very quickly, what do people think is the L1 fixed array to storage slot? 6. Is it 6, 7, 8, and 9 though? Why is it not 6, 7, 8, and 9? Sorry? It comes up to you in 256. Yes, that's correct. So actually this occupies like one storage slot by itself. So just storage slot 6. Again, I feel like the reference from the visual representation, visual illustration from Peter using like Foundry to check out this storage slot, that is like really helpful to also look at it. But this is also us going through the example, through the lenses of like Remix and see what we can actually identify. So the storage slot here for L1 dynamic array, it is actually, yes, storage slot 7 then. So for us to access the storage slot 7 over here, we're gonna pass 7 as the input, and then for array index here, it's going to be 0, and then when we call it, we're going to be getting 100. And 100 matches with what we've instantiated also as 100 over here. But the way that it is, the way for us to actually sequentially call the variable, the information of, in this case, the uint256 information, we're going to be adding incrementally +1, because that's how the information is packed in the storage slot. So it gets hashed, and then it gets typecasted uint256. Every subsequent number that gets pushed onto that array, it will be occupying that slot respectively for the value. So even though when we push new information on top of dynamic array, that is, we just have to add a subsequent new increment +1 to array index, and we're able to access that information and fetch it. When it comes to decoding this data, it's really, I would say, the same type of syntax that we see for retrieve L1 number. It's ABI decode, data, and uint256. Moving on to the next one. I think mapping is an interesting one, but because this example here, L1 address to mapping, this is fairly straightforward. We have the L1 address to number mapping, which maps this contract, which was instantiated already. The same address will then give you a value of 100. So with respect to time, I think I only have 20 minutes left. What I will do is everyone will be able to like reference this information over here. I will skip through retrieve L1 address to mapping, but instead we're gonna go through a cooler example, which I think has seen a lot of use case and a lot more interest, which is when we're trying to retrieve and resolve ENS handle. There was some feedback mentioning that there were a lot of nested mapping used inside of ENS contracts. Some of the feedback that we've also gotten was that it was relatively over-engineered. I'm not too sure, but to some extent, we would use L1SLOAD, gives you the capability to access and resolve your ENS handle at L1, at layer 1 itself, right? So for this function, when we call the retrieve L1 nested mapping, this will be a bit more interesting in the sense that we have mapping address as a variable and also mapping string. And where do both of these arguments come from is that if we look at nested mapping here, where do we go? So for L1 nested mapping, it's essentially like an address that maps to another mapping of string to then finally resolve it to a uint256. So for us to resolve to the final uint256 result, there's like multiple ways that we have to first hash the slot in order for us to access that information. So because there is 2 levels of mapping over here, I would say, so we're gonna have to first hash the initial slot, and in this case would be like catch up to 256, and then similar syntax, ABI encode pack, We have our uint256 here with the mapping address. Mapping address, this will be the address that maps to this new mapping of string to uint256, and we're going to have to like pass on the variable storage slot. Now, do note that in this context over here, you will notice that this method of concatenation is that the variable storage slot comes later after the mapping address. So the way of hashing it, the way of accessing mapping is that we first structure the input, I would say to the left, and then the variable storage slot like to the right over here. And then as you have multiple levels of mapping, you would add on additional levels here. So for example, like bytes 32 initial slot, and then maybe like bytes 32 like second initial slot, and so on and so forth. And then once we have the final slot over here, we're just passing the final slot information into our low-level call. And then since it's a uint256, we're then able to like decode this information directly. So let's give this a try. Over here, for L1 contract, we have initiated it with this address, ABC, and also 1000. And it should be returning a value of 1000. So this L1 contract, it is over here. And we have retrieve L1 nested mapping here. We will pass on the address here first. And again, for L1 contract, this is storage slot 7. So we'll pass on 7 here. And for string, what's for string? ABC. Let's do ABC. But when we call with ABC, we're getting a value of 0. Does anyone know why? Okay, I'm getting everyone to like doze off. So let me answer the question, because we're gonna have to follow exactly, more like a checksum thing, I would say, where we have to follow exactly what was being passed. In this case, it's supposed to be like an ABC. Let's see. And then we have this call. Then we should be able to retrieve this information. Let's see. Contract address. Oops, that is not storage slot of 7, because for nested mapping, it goes to 9. When we call it, there we go, the value comes up to 1000. So for those of you who are interested in understanding how to access nested mapping, this is a good example for you to start diving deep into. For the last example, I know I only have like 17 minutes left. I'm going to like speed run this. So for the final function here for retrieving struct, this is actually the same one. We have seen the same syntax like previously, and this actually goes back to mapping. So when we look at how the mapping for, there we go, gone through here. So for mapping, no, not mapping, my bad. This is with array index. It's very similar because the way that it is, yeah, so for like dynamic array number, the way that dynamic array stores its value, the way that it accesses the storage slots, dynamic array, they're very similar to struct. Actually, exactly the same. So for example, I'm going to showcase a quick example over here for retrieving struct. The variable storage slot, we're going to look into this again. We have 7 here, and then for address to number, we're going to say 8, and then here we're going to say 9. But for L1 profile struct, do we think that this also occupies a storage slot? No, the answer is no, so I'll say no. And then over here, it's actually storage slot of 10. And finally, over here, if we were to showcase the example of this, whoop, so for retrieving struct here, it's going to be variable storage slot of 10. And if we pass in 0 as the array index, we'll be able to get this value in bytes. But this is so interesting because the payload that we've defined, it comes out in bytes. So this could be like a homework for everyone to kind of like test it out, because this contract is already written. You can see that how you can access this information. But I've also created some utils over here for us to convert, for example, like bytes to string. So if I pass the bytes value that we've passed in, you can see that it returns like Alice in this case. So these are basically just like a set of contracts already written in Solidity for us to see what it is like implementing and trying to extract information from L1 using 2 different types of data types and 2 different types of data structure. So yeah, this is all I have. Does anyone have any questions? Or do we want to like go through everything first, then take questions like, later? Yeah. Yes. Using the gas cost. I remember reading that there were some, but maybe I'm going to like get Peter to also like, but for like a general call, usually there's no gas cost. Yeah. But I do remember there was also a topic on this, but I will lean on to like Peter to also like talk a little bit about this. That's a good question. Thank you. Oh, yes, you have a question. Yes. Come again? You.
Live on L2, like would L1 be aware of the existence of this? Okay, no. And the other thing is that,
Yes.
I remember in the first presentation was mentioned proof of inclusion, and I was wondering why is it necessary with like to some machinery? I guess you read something that you know that exists in the memory, or somehow like, and also this proof of inclusion is something that is generated within this precompile.
Is it okay if I?
Yes.
Yeah, so we can probably spend the rest of the time on questions. There are some interesting questions in the form too. So I believe your question, maybe there were two questions, but the second one was, why do we need to have all this MPT verification?
Yeah, basically, if I read the memory of the source of like some stuff that is written on chain, even if it's on a different level, like I know that it's there, why do I need a proof? And then if this proof is generated inside the compiler.
Yeah, so you as the L1, if you run an L1 validator, you know exactly the state, but you as the L2 node or you as the L2 contract, you don't. So what that means is the sequencer returns some value to you, to the contract caller, but the sequencer could just make up a value. We don't want to allow that. So that's why the sequencer, as part of the verification, could be fraud proof, could be ZK proof. It must provide a valid proof saying that, hey, I gave you this value and this is the actual value stored in L1. It's much stronger than an oracle. I guess, so I would say the sequencer optimistically relays this information. At this point, you can view this as an oracle, but you also verify it eventually. So there's like a period where you cannot trust the sequencer, and then eventually you verify it, so the sequencer long-term cannot cheat.
For example, if we are on the same layer, I can read the memory over the storage of another contract, right?
So if you have two contracts, let's say on the same blockchain on L2, if one of the contracts exposes the storage, let's say a view method, then you can read it. If it doesn't, then you cannot. So usually you would need to call RPC. So that would be another interesting proposal, just letting you to read arbitrary slots from other contracts. Maybe that's a bit too invasive. It's useful for as a building block between L1 and L2, I believe. But for L2 to L2 applications or L1 to L1 applications, I'm not sure if this is super useful. Yeah, the proof of inclusion is just a verification. So that's kind of the second step. I think there's a related question before we go to other questions. Someone asked, can I utilize L1SLOAD to call a view function on a contract? That's an excellent question because there was another proposal that's called L1 call, which is exactly about that. So you would call this also a precompile from your L2 contract, but instead of this very low level access to storage, you would trigger a view function, which is much more powerful and safe in a way. The problem with that is that it's much easier to verify it. So for instance, scroll, we have a type 2 ZK EVM currently. We have our own prover, and it works for scroll. But for L1 call, you would need to spin up like a whole different execution environment, a type 1 ZK VM, and create a proof for that single call, and aggregate that proof together with your original proof. It's not impossible, but I don't think it's practical at this point. So L1SLOAD kind of fills the gap of giving you something useful and practical, but it's not as convenient as a call. I think we had a question somewhere there. If not, yeah, go ahead.
That's the one from the top. So about security, how confident can we be in terms of L2
Yeah, so that's one of the prerequisites that I said is that the L2 should have a notion of the latest L1 block. And the way we would implement it is that the sequencer of scroll relays blocks from L1. Now, how recent these blocks are is kind of a security parameter of the system. If you wait for finalization, that's the safest, but then you have to wait. There's like a delay of relaying information of like 10 to 15 minutes. If the sequencer is waiting for a couple of confirmations, then there must be a mechanism in the rollup that reorgs if L1 reorgs. So
is the L1 block hash part of L2 block, or how do you, because at the end you need to do the proving, right?
right, so the sequencer relays the L1 block hashes to L2. So basically, you could also read directly the L2 state root or the L1 block hash, sorry, L1 state root and L1 block hash from L2 state. And that's what kind of L1SLOAD gets access to. But it's a very valid question. Actually, that's one of the open questions. Like the sequencer could just stop relaying this information. Currently, there's no mechanism to force the hands of the sequencer to keep relaying information. So it's possible that you read stale information. We need to do additional work to support applications where this could break them. But in most cases, you could assume that the data that you read is maybe 5, 10, 15 minutes ago from Ethereum. Another question? No worries. Just a few. I think we're about to wrap up. I don't want to take any time from the next section. Just. You mean the roadmap? Like moving on, or? Yeah, so we do have an implementation, and that's what I linked before. So we do have this DevNet, but it's not production ready yet. So that's why it's only a DevNet. It's not part of our testnet and mainnet. There's still a few rough edges that we need to figure out, and also we don't want to deploy it on mainnet until at least 2 rollups adopt it. Like this is only really useful if multiple L2s support it. And to say why, I just want to mention that we have a third example that we didn't get to today. If you open the repo, then you can see it, and it's a key store. The idea of the key store is that you know we live in a multi-chain world. So you might have your wallet, your AA wallet, some whatever you prefer on multiple chains, and it's usually a multisig, so you can have multiple signers, multiple keys associated with it. Now in this multi-chain world, this becomes very inconvenient to maintain. If you want to add the key or remove a key, you need to do this again and again for all of the chains, and it can be 5, 10 different chains. So the idea of the key store is that, let's say you have a key store contract on L1, and the whole purpose is to manage keys. You can add and remove keys, and all your wallets that are deployed on, again, Optimism, Scroll, Arbitrum, they read which are the authorized key from L1, and they just use this. So you can update it in one place, and it automatically updates with some delay on all these other chains. So that's kind of to show an example why it's only useful if it's multiple rollups that's supporting it, because these use cases are really unlocked by this feature. Yes, so each of the rollups will need to implement it, and because rollups work differently, there might be, so the specification and the interface would be the same, but the details of how it works might be different from rollup to rollup. So that's kind of an implementation detail that's left to the rollup team. Apologies, there's a bunch of questions that we didn't have time to answer. If any of you are interested, either devs or protocol maintainers who are interested in adopting this, I'd love to chat with you. So find me anytime after this session or later. And we also have another session on Thursday, 5:50 p.m. about the same topic. That's all for today. Thank you.